Hey students, I have put this video together to give you a little reminder of what we've covered in waves so far. The first part is that waves are defined as a wiggle in space and time. And some wave characteristics that are important to know is that wave carry energy and transfer energy. And then some waves require a medium to go through and some do not. And we're going to talk about those types of waves in the next few slides. When I talk about a medium, it is the object that a wave is traveling through. We just did a Slinky Lab, and you guys know that you had to create a wave by shaking your hand, and the medium would be the Slinky. Other types of medium would be water, when you see waves in the ocean, the air, when you are having sound waves travel through the air. Those are different types of medium. And of course, we did our Slinky Lab and realized that between the more dense metal Slinky versus a plastic Slinky, the density is important. And we learned that the greater the density, the slower the wave moves. And that's for certain types of waves. We're going to learn when we get into sound that the higher the density, the faster waves move. So it changes depending on the type of wave. There are two types of waves. I didn't talk about the first type, but the first type is electromagnetic waves. These are waves that we can't see, and these are waves that don't need a medium to travel, but they can also travel through a medium. So they're very versatile type of waves. Some examples are light waves, radio waves, and X-ray waves. The second type of wave is the mechanical wave, which is the waves that we've been talking about so far. These are waves that we can see or feel their effects, and they do need a material or a medium to travel through. So we have talked about water waves. We cannot see sound waves, but we can definitely feel the effects of sound waves. When you have a loud beat, you can feel the beat in your environment. And also we obviously have the Slinky, which we did a lab on. Okay, here's a quick little warm up. We just talked about medium and what it means. So I want you to go through the list and cross off any of the items that are not a medium. We've got metal, dirt, water, wood, rock, cement, air, or space. This is objects that mechanical waves are able to travel through. So if you crossed off space, you are correct. Obviously, we said air was a medium, water was a medium. Any physical object would be a medium. Space is a place where there is no air, and it is therefore a place that mechanical waves cannot travel. This is the reason why we are not able to hear sound in space, which may be contradictory to the movies you've seen, but you actually can't hear sound out in space. You can see light, which is why we can see stars and the sun, but sound actually does not travel through space. Something important. Medium is made of lots of individual particles. You guys know that all objects are made of tiny little particles and that they vibrate in response to a wave traveling through it. The particles itself do not move with the wave, they just vibrate in response to the wave. And then a pulse is a single disturbance in a medium rather than a continuous wave. So when we did the Slinky Lab, we wanted to create one single disturbance or one pulse in order to see the speed of the wave traveling along the Slinky. Here is an example of people doing a wave. This is a mechanical wave, and I wanted to show you this example simply because this example shows how particles do not move with a wave. So you can imagine the people as the particles. So as you watch this wave traveling through, notice the people move up and down as the wave travels past them, but they do not go side to side as the wave travels side to side. So this is the example of how particles move when a wave travels through it. So here's a little graphic organizer to help you understand the different types of waves. We've got electromagnetic and we've got mechanical. And we're going to focus on the mechanical waves and talk about the different types, which we already talked about in class. So the different wave parts of these types of waves are the wavelength. It is the distance before the wave repeats itself. So we would go from peak to peak, or as you will learn in a second, crest to crest. And the variable that you use to represent wavelength is called lambda. Crest is the peak or the highest points of your wave, and trough is the valley or the lowest points of your wave. The amplitude, as we've said, is the wave's maximum displacement, so the maximum distance from the resting point or equilibrium position of your wave, and it correlates to the amount of energy that is in your wave. So here's a transverse wave. I have a great visual to show how the particles are vibrating perpendicular to the direction of the motion of the wave. So I want you to focus on one particle and notice how the particle simply moves up and down as the waves travel through, the same way that the people moved up and down in a stadium as the wave travels through. So the particles don't move left and right, even though it seems like it does. It actually just moves up and down in response to the wave vibration. This is another visual of a transverse wave, more 3D version. And then another picture of a transverse wave. Now, labeling all the parts is really important to know. So we've got a wavelength, we've got the crest and the trough, so the peak and the lowest point. And then I want you to be able to practice drawing these different parts. These are longitudinal waves. So longitudinal waves travel across, and the particles move left and right, but notice how the particles don't actually move all the way across the extent of the object. It just moves back and forth as the wave travels past it. So this would be a picture of a longitudinal wave. It is a vibration that moves parallel to the medium that it is moving through. Longitudinal waves have compressions, which is the high density points, and they also have something called rarefactions, which is the less dense periods in your longitudinal wave. Here is another example of a longitudinal wave. It's represented in a slinky, and we did this with the Slinky Lab. You can see the compression, and this has multiple pulses, but we had one compression traveling up and down. And then here is our rarefaction, which is where the slinky is most spread out. A wavelength would go from compression to compression or rarefaction to rarefaction. And then another example of a longitudinal wave shows here more in higher density shading, where you can see a wavelength in the high density areas and then a wavelength in the low density areas. And this would be your compression point, and this would be your rarefaction point. Surface waves we've talked about also. These are types of earthquake waves. They can look like surface waves. These have both perpendicular and parallel movement. So notice how the particle itself goes circular. So it goes up and down, then left and right in a circular type of motion. So that basically covers everything that we've learned about waves so far. Hope this was helpful.